Hey everyone, welcome back, and today let's solve Leetcode problem 2257 titled Count Unguarded Cells in the Grid. So we're given two integers m and n representing a zero-indexed m by n grid. And we're also given two 2D integer array guards and walls where guards at I represents the row at that index and the column value at that index. And walls at index j represents the row value at that index and the column value at that index, right? It's simply going to represent, again, the positions of the ith guard and the jth wall respectively. So a guard can see every cell in the four cardinal directions, right, which are just north, east, south, or west, or in other words, four directionally adjacent cells, either up, down, right, or left, starting from their position unless obstructed by a wall or by another guard. And a cell is guarded if there is at least one guard that can see it. We need to return the number of unoccupied cells that are not guarded. Okay, so in example 1, they also give us an image to better visualize how this example actually works. We have m to be 4 and n to be 6. That's just telling us that our grid is actually going to be, or having dimensions of 4 by 6. And we have our actual guards and walls positions, right? This just tells us where or which indices and cells our guards and walls are actually positioned, as we can see in this input example image as well. And we output 7. Why is that? Because they actually tell us that the guarded cells are going to be in red, while the unguarded cells are going to be highlighted in green, okay? And there's going to be a total of 7 unguarded cells, right? As you can count the number of green cells, which are just unguarded, and so we need to return 7. Right? They are the number of unoccupied cells that are not guarded, right? The value of that is going to be 7. And note, why are all of these cells green? Well, that's because they don't actually have any guards actually looking at them. Okay, right? That tells us that they're not guarded. Okay, or rather, sorry, that tells us that they're unguarded or not guarded. Okay? So in example 2, we have our input grid to be the following with dimensions m by n, or 3 by 3 in this case, it's a square, and we have our positions for our guards and the positions for our walls as well. Now, we know that a guard cannot see through a wall. A wall actually obstructs a guard, and so for that reason, these 4 cells are going to be all green, right? All of these cells where a guard or wall is not there are all going to be green, right? Because of course a guard can only see 4 directionally adjacent cells. In this case, all of those cells are walls, and so this guard right here would not be able to see these cells, right? These unoccupied cells that are unguarded. Okay, and so for that reason, we would output 4. And so with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so the way I'm going to solve this problem is actually first initialize the grid using our m and n dimensions given as inputs. Right, we're going to actually represent or initialize this grid as a 2D list, where again 0 is going to represent an empty cell, 1 is going to represent a wall, I'll make 2 represent a guard, and have 3 represent a guarded cell. Right, and we're simply going to actually place our guards and walls onto the grid that we just initialized, where we just basically iterate over our actual given lists of guards positions and walls positions to actually place them at their corresponding indices or cells in our initialized grid. Okay, then we have to actually mark all of our guarded cells, and the way we can do that is simply we check for each guard. We have to actually kind of stimulate marking all of the cells in the 4 directionally adjacent cells, which are up, down, left, and right, and stopping at walls or at any other guards that again obstruct the guard from looking at that cell. Right, and then we have to actually just remainingly count the unguarded cells and return that value, right, by simply just iterating through our grid to actually count all of the unguarded cells, which are just all the cells still marked as a 0, because again, note that a 0 represents an empty cell that we haven't actually changed or marked. Okay, so with that out of the way, let's go ahead and actually initialize the grid like we were just talking about. So I'm going to set grid right? This is the grid that we're actually initializing. We're using our m and n dimensions. It's going to be equal, or rather initialized to an array of 0, and it's going to be multiplied by n for, and in this case, I'm not going to use my iterator in this for loop, so I'm just going to use an underscore for a placeholder or a place filler in the range of m, right? It's an n by n grid, okay? Right, where again 0 is empty, 1 is a wall, 2 is a guard, and 3 is actually a guarded cell, right? It's going to have m rows and n columns, right? And we're going to again initialize all of these cells in this 2D grid to be 0, right? It's going to be that number of zeros based on these dimensions n and m. Okay, so once we've initialized this grid, now let's actually populate it with the corresponding guards and walls based on our inputs, guards, and walls list. So for x and y in our walls input array, this is unpacking in Python. The reason why this works is because we know in our walls input to the list, for each element, we're going to have 2 elements in each list. And so for that reason, if we use 2 iterators, we're going to have x correspond to the initial index or the initial value in each list for every iteration, and y is going to be initialized to the second value in each list for every iteration, right? Where we simply use x and y to be the first and second values of each list as we traverse over them iteration by iteration, or again, level by level in this for loop, right? We're simply going to basically in this grid update this corresponding cell at index x, y to be 1, right? Because again, for each wall position at index x, y, we need to actually update our corresponding cell in the grid that we initialized to be a wall at that cell, because that's where that's what the wall's input tells us. The indices are cell values where we have walls, and so we have to update those cells to be walls in the actual input grid. So for x and y in the walls input array, simply just telling us the coordinates of the cell values of our walls, we need to set grid at that index x, index y, or rather cell index x, y to be equal to a 1, simply representing that it's a wall, and we know it's a wall because it's a coordinate or cell value in our wall's position input 2D list. And we have to do the same thing for our guards to actually place our guards accordingly on their corresponding cells in our input grid that we initialize. Okay, so for x and y in the guards, similar approach. In this case, instead of initializing all of these values at these corresponding cells to be a 1, we have to update these cells to be a 2. So we'll set grid at index x, index y. In this case, instead of being a 1 to be a 2, right? We have to actually update it to be a 2 for this corresponding cell, because again, this guard's position is going to tell us at which cell values or indices x, comma y do we have a guard, and we have to put a guard or mark that cell correspondingly in our grid that we made to be a 2, where again 2 represents a guard, which we can actually use as we actually kind of scan through this input grid to check where we actually have unguarded cells and return that value. Now I'm going to initialize a helper function to actually check to actually mark our guarded cells and check how many cells we have to actually have that are unguarded. So I'm going to call it mark guarded. Pretty self-explanatory here for my helper function, and I'm going to take in 4 parameters. The first 2 parameters are going to be x, comma y, and my second 2 parameters are going to be dx, comma dy. Okay, we're going to have 4 parameters, right? And it's simply going to be used to actually mark all of these cells in a particular direction, again dx, dy, as guarded in our grid that we initialize. Okay, so once we've done that, now let's actually have our initial kind of boundary check. So while x is greater than 0 or equal to 0, and rather I'll have the and after, it's less than m, it should be strictly less than m, and we have to have the similar logic for our y coordinate, or rather index value is within the number of columns, right? What is this checking? This is simply making sure that our current cell with position x, comma y is basically within bounds of our array. Our x or row value for this current cell is within bounds of our actual grid. So it's at least 0, right? Because we don't want to have negative indices, and it's strictly less than m, the number of rows that we have, okay? And our column value for this current cell index or cell value also has to be within bounds. So it has to be at least 0, it can't be negative, and it cannot be greater than n. Right? And sorry, this should be simply less than, not less than or equal to. It cannot be less than n, which is the number of columns we have, simply making sure that our current cell that we're marking is actually within the grid bounds. And again, it has an actual position of x comma y. That's the cell index. Now we have to check, well, is our grid at index x, index y, is it actually a 1? If it's a 1, or if index x, index y, if it's a 2, right? So if it's a wall or a guard, then we have to immediately break out of this iteration. Why? Because if the current cell, again, contains a wall, or the current cell is a, okay, sorry, I forgot to type 2. If it's actually a guard, so if it's 2, we have to actually start marking cells in this direction and break out of this iteration, right? That's just the kind of stop condition for this loop. But if the current grid at index x, index y, if it's actually a 3, or rather, sorry, a 0, then we have to mark it as a 3. Or rather, this should just be 1, right? So what does that mean? Well, if our current cell is 0, and like we talked about before, we initialized grid to be 0, so if our current cell is 0, if we never updated it to be a wall or a guard in these for loops given in guard and wall inputs, so if it has still remained by this iteration an empty cell, we have to then mark it as guarded, okay? Where again, 3 is simply marks all the cells that have been marked as guarded, right? We're simply marking this cell at index x, index y from an empty cell to be a guarded cell. And once we've done that, then we have to actually increment x by the dx coordinate and y by the dy value, okay? We're simply just updating our current cell's position or index x comma y to that next cell in our given direction, dx and dy, okay? So now let's actually iterate over our guards array and simply just loop through all the guards to make sure or mark the cells that they can see from their position. Okay, so for x and y, again, npacking in Python using 2 iterators in our guards input array, again, we're simply just marking the cells that all the guards can see for their corresponding cells. We're going to actually kind of call our helper function at the cell for the 4 directionally adjacent cells, up, down, left, and right. So we're going to call mark guarded. Again, note that this is our helper function that we defined. And for our parameters, we're going to have x minus 1, right? Again, x comma y is the current cell. We're going to have x minus 1. We're going to have y. We're going to have -1. And we're going to have 0. What does this mean? We're simply calling mark guarded, and we're going for the cell that is up, right? That is up or north of our current cell. Okay, our current cell x comma y, and we have to again call mark guarded for the cell down, right? We've done up, now it's best to do down. So in this case, it's going to be x plus 1. We're going to have y still, right? Our y coordinate doesn't change. We're going to have 1, and we're going to have 0. We're simply just calling this mark guarded function and marking it as guarded if it passes these conditionals for the down cell. Again, that's one more of the 4 directionally adjacent cells from the current cell that we're iterating through or parsing through x comma y. And then we have to actually call this helper function and mark it as guarded for the left and right cell. So I'm going to call mark guarded. And note that these calls are all being done within the loop for every cell x, y in our guards input array, right? So we're going to have x, and in this case now our y values are going to change because we're going left and right. We have a horizontal shift now. So first I'm going to pass in y minus 1, and I'm going to pass in 0 and -1. Oops. Okay, and similarly I'm going to call mark guarded for the right cell. So it's going to be x, y plus 1, and I'm going to have 0 and 1. Okay, this is simply calling the mark guarded function on the left 4 directionally adjacent cell from the current cell x comma y in this for loop or iteration, and this is going to be for the right cell of the current cell x comma y, right? For each guard, we're simply calling this mark guarded in the 4 directionally adjacent cells to mark them as guarded. And once we've actually marked all of our kind of corresponding 4 directionally adjacent cells for every guard to be guarded if it fits the criteria of not actually being unguarded, then we can simply return the sum of what are we actually returning the sum of. It's going to be this, just a quick warning, this is going to be pretty Pythonic here. I will explain how it actually works after. Just let me kind of finish coding it out, and you guys will see how it really works. So we're returning the sum of 1 in the range of m, right, the number of rows we have, and this is going to be this kind of computation with the number of operations we're doing for this for loop are going to be in the range of n, the number of columns we have, if grid at that index ij is actually equal to a 0. So if it remained after all of these iterations an empty cell, we didn't mark it as guarded, it remained empty, meaning it was actually unguarded, because we again want to return the number of cells that are not guarded. So we can only return the sum of all the different cells if it's equal to 0. Again, if it's equal to 0, that means we haven't actually marked it as guarded, or it wasn't ever a wall or a guard in the first place. It was empty, and so it was an unguarded cell, right? We're simply using nested loop. In this case, I can call it nested loop comprehension in Python, and we're doing this to count all of our cells in our grid that are still 0. In other words, that are still, again, unguarded, right? We're simply returning the sum of all the different cells, which is going to be a 1 for each cell, or a value 1 for every cell that's unguarded in the range of the number of rows by the number of columns. Simply just nested loops to actually iterate over all the different cells in our input grid that are equal to 0. Technically, I could have kind of made this a little bit neater using nested loops and checking if it was equal to 0 and incrementing a res or some running total value of the number of unguarded cells by 1. This is a little bit easier. I don't want to say easier, but quicker to do it using one line, right? We're simply just returning the sum of, again, 1, right? We're incrementing 1 by each time for every single cell grid ij that's unguarded or empty, that has a value of 0, right? And for every cell we do this, we increment the value by 1, and we're taking the sum, right, which simply just tells us the number of ones, or the number of cells, ones for each cell, that we're actually adding to our final result that actually have cells that are equal to 0. In other words, that are unguarded. And that's going to be it. That's actually all of the code. So unless I made any syntax errors here, this should be accepted, and this should be a valid solution. Okay, let's check what I did wrong here. Sorry, I don't know why I have an and here. This should just be for x, y in guards. I don't know why I had an and keyword in that loop. Okay, let's see here. Okay, yeah, this is one more of my goofy bugs. There should be a 0, not a negative sign. Probably made another error here. Let me just check. But as you can see, this is just about as efficient as you can get, both runtime complexity-wise and memory complexity-wise. You can clearly see that we're pretty efficient here, beating 72% of users runtime complexity-wise and basically just 100% of users memory-wise. So, kind of just a quick reiteration of what this code does overall, a quick high-level rundown of how I actually kind of went about this. Well, we're simply just initializing our grid based on our given input dimensions, n and m, the number of rows and columns we have, right? And then we're actually placing or initializing the guards and walls, right, which are given in the guards and walls input list, right? We're simply using those actual positions in our guards and walls input list and marking all of the cells at that corresponding indices to be 1s or 2, based on if they're guards or walls in the grid that we initialized, right? Then we have to actually use our helper function to simulate the guards marking cells in their line of sight, right? In their 4 directional adjacent cells line of sight. And after we actually process all of the guards, we can simply just count and return the number of unguarded cells that are still equal to 0. Once we've called this helper function on every single 4 directionally adjacent cell when it's actually a guard, and marking it as guarded if it actually is a guard, right? For its line in sight if it's not being blocked by another guard or a wall. And we're simply returning the sum of the number of cells that remain 0 or that remain empty and not marked as guarded for any of the guards in their line of sight. So for the time complexity of this solution, this is going to be a big O. Actually, I think this is pretty complicated, so I'm going to type this out. The time complexity here is going to be big O of, okay, sorry, I should have O here, of G times M times N. And what does this actually mean? Well, let's kind of break it down to understand how we get each of these corresponding operations or times. Well, for us to actually place the guards and walls in our grid, that's going to be a big O of G plus W operation, where G is going to be the number of guards and W is going to be the number of walls. Again, this is simply going to be to place all the different guards and walls in our input grid. And to actually mark our guarded cells in our input grid, as we call this helper function, and actually call it for every cell X, Y in our guards input list, that's going to be a big O of G times M times N, since our guards may possibly, at worst, traverse the entire grid, right? It's going to be the number of guards times the dimensions of our input grid, right? G times M times N, where M by N is the dimensions, or the number of rows and columns respectively in our input grid, rather not input grid, but grid that we initialize based on our parameters m and n. And to actually count our unguarded cells, that's also going to be an extra time complexity of big O of m times n. And so the overall simplified time complexity is going to be big O of g, the number of guards, times the dimensions of our input grid, m by n, right? We're simply iterating through all the cells in our guards input array and calling mark guarded, which at worst could traverse the entire grid. All the guards could traverse the entire grid if all of them are in their line of sight. So for the space complexity, it's going to be pretty simple here. It's just going to be, okay, sorry, I forgot to comment this out. It's simply going to be a big O of m times n solution. You guys can probably figure out why that is yourself. In fact, I would encourage you to do that before watching how I would explain it. And again, the reason why is because, of course, we actually have to initialize and store all the different cells and their corresponding values in our grid. The grid is going to have the same dimensions, exact same dimensions as n and n, right? We're literally build this grid off by the m by n dimensions, right? The number of rows and columns, which are given as inputs, which has dimensions or an area of m by n, and so the overall space complexity is going to be big O of m by n. We're not using any extra data structures besides this grid that we actually make using our input m and n dimension or integer values. So that's going to be it for today's code. I hope you guys enjoyed this solution and learned something new. And if you guys enjoyed this solution, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.